So our idea is that we take this white dwarf, put too much mass on, we won't worry for the moment about why, we'll come back to that, and it shrinks, and that brings the density so high in the middle that you can fuse carbon and oxygen to form iron. We know that iron is the most stable element, it's at the top of that curve.
Yep.
So let's look in some detail about how this will work.
So let's think, if you try to burn carbon and oxygen, especially when it's really dense and presumably when it burns it's going to be pretty hot, let's just look at what happens within stars or anything with nuclear binding energy. Most of us will see this. If you measure what the mass is and divide it by how many nucleons, that how many protons and neutrons there are, and you plot that, then you can go through and you find that there's this maximum spot where iron is. Iron 56 is sort of the maximum of that. And so that means that whenever I'm going to fuse two things together, I maximize my energy when I reach iron.
Yeah, so we talked about this before. So we said a normal star like the Sun is taking hydrogen up to helium, and then maybe at some later stage will bring it up to helium here, and that would be that gives you a lot of energy.
Yep.
There's rather less energy to be gained going from there to there, but there's still a reasonable amount.
But if you overshoot this, so imagine the star would overshoot that, well, that takes energy away, and it's going to want to fission back. So the natural place for you to end up when you burn something really fast with nuclear power is up here, if you can get there. And it turns out, if you do detailed calculations of these things, that's exactly what happens. You end up burning to what we call the iron peak. Now, in detail, if you go through and do a full calculation, and this is what the guys at the bomb labs are really good at doing, and here we have a very high density and very high temperature, and for almost any sensible temperature, you end up making this stuff we call nickel 56. So that's nickel rather than iron, 28 neutrons, 28 protons. Now it turns out that iron is two neutrons and protons different. So this is something that turns out is radioactive and can end up eventually making iron. But it's the place that these nuclear reactions want to go, because it turns out it's neutral with its charge, and that's turns out where the nuclear reactions like to take it.
So we've got this white dwarf, it's gone over the mass limit, and then presumably the centre is going to start, and you're turning the carbon oxygen to nickel 56. That's going to generate a lot of heat, presumably.
It's going to generate a lot of heat, and of course, if you think about that, let's just say we have this star, and we start burning stuff up to nickel 56 in its core, so like that, then this is degenerate again. So if it's a degenerate gas, we know that temperature and pressure are once again sort of independent, so unlike what we're used to here on Earth.
So it can start burning in the middle and gets very, very hot, but the pressure doesn't go up, so it doesn't cause anything to expand, doesn't throw a blast wave out or anything. But that enormous heat will then presumably start fusion further out.
Right, so you could imagine that what would happen is that you would sort of catch fire very quickly, sort of faster than the speed of sound, and that the whole thing would burn to iron almost like that. You end up with this huge ball of iron.
Or nickel 56.
Of nickel 56 in this case. In our case, because that turns into iron, it turns out nickel 56 is radioactive, and it turns in first to cobalt 56, which is also radioactive, and eventually to iron 56. And so the half-life of this is about a little more than 6 days. And each time it does that, it lets out a lot of energy. So we measure things in MeV is sort of the...
That's a mega electron volt. We talked about electron volts in the first course.
And that's a little bit, it's about 10 to the minus 13 joules per each one of those decays. And so that turns out to be a lot of energy. So when you create that big ball of nickel 56, you're actually creating a huge release of energy. And so it's like you've suddenly released all this energy into this ball of gas. And what do you think that ball of gas is going to do when you do that?
Well, I mean, normally think if you put much energy into a ball of gas, it will get bigger, but this is a degenerate, so it's not clear that actually happens.
Well, it's not going to be very degenerate after it does all these nuclear reactions, it turns out. So the degeneracy, the nuclear reactions that happen, get rid of the degeneracies. So once again, temperature and pressure are related, and you suddenly have all this energy stored up in this ball of gas, which is no longer degenerate.
So would you actually call this a fusion bomb, or is it a fission bomb? Because you're getting lots of energy by going up the curve from carbon, oxygen up to nickel.
Yep.
But then a lot of the energy is coming as you then break nickel down to iron. So where's most energy coming from? Is it going from the first step or the last step?
Well, the energy is created in the what we call a thermonuclear detonation that creates the nickel 56, but then it's actually released, the stuff that we actually end up seeing is released by this radioactive decay as a fission process.
So the first step, when you get to the nickel 56, produces large amounts of energy, but that energy is stored in the form of these highly radioactive elements, which then release it as they decay.
That's correct. So it's an interesting process. And of course, the cobalt, also radioactive. Now, it has a half-life of 77 days, so more than, 10 times longer than that. And it produces more energy per each of those decays. So you might think that this would be more energetic, but because it's happening slower, there's actually a bigger pulse of energy here.
So there's actually more energy there, but lower luminosity because that's spread over more time.
Right. So if you go out and let's look at one of these Type 1a supernovae and see how much energy they put out, this is what we call a bolometric light curve. We talked about them earlier. It tells you the total luminosity in astronomers' units, ergs per second. So if you divide by 10 to the 7, then you're in watts, which is maybe a more sensible unit. And you can see that they produce a bit more than 10 to the 43 ergs, or that's 10 to the 36 watts, over a period of a couple weeks. So let's go through and figure out how much nickel 56 we need to create that light curve.